Hello, in this video we're going to talk about Leslie matrices. And so to begin, we're going to talk about beetles, and we're going to talk about beetles that come in age classes. So we have very young beetles here that are between 0 and 1 year old of age, and then we have beetles that are between 1 and 2 years of age, beetles between 2 and 3 years of age, and lastly our adults or very mature beetles between 3 and 4 years of age. Let's begin with an initial vector, and we'll assume that in our initial vector we have a certain number of beetles in each of these different age classes. So suppose we have 30 newborn beetles, 35 juveniles, 25 young adults, and 10 very mature beetles. Now, we're given some other information as well. Suppose that we are also given some information here about a breeding rate. So suppose that we are given that our 0 to 1 year olds, they do not produce any offspring. And the beetles, which are between 1 and 2 year olds, suppose that on average they produce 4 offspring. Our beetles that are between 2 and 3, suppose they produce 2 beetles on average. And then our very mature beetles, on average, they only produce 1 surviving offspring. In addition, let's suppose we're given some information about survival rates. And for our survival rates, suppose that we have 0.7 chance of survival for the 0 to 1 year olds. So those young beetles have only a 70% chance of surviving their first year. We've got a 50% chance of survival for the 1 to 2 year olds, 20% chance of survival for the 2 to 3 year olds, and a 0% chance of survival for the 3 to 4 year olds. Now, if we wanted to compute how many 0 to 1 year olds there will be, it would look something like this. So let's write this down. After 1 year, how many 0 to 1 year old beetles will there be? Well, the only way you can get a beetle that's between 0 and 1 years of age is if you have a newborn beetle. So this is equivalent to asking, how many newborn beetles do we have in a given year? Okay, so we need to add up. Our very young beetles, so the beetles which are from 0 to 1 years of age, we have 30 of those beetles, but if we go back up here to our breeding rate, they have a 0 breeding rate. So that's going to mean that our 0 to 1 year old beetles do not produce any new beetles, so they don't contribute to the number of newborns. The beetles from our age category 1 to 2 years of age, let's see, we had 35 of those beetles, and their breeding rate turned out to be 4. And so what we expect from them would be 35 times 4. Next, we've got beetles from the age class 2 to 3. We had 25 of those beetles. Their breeding rate was 2, and so that's 50. And lastly, we had beetles which were between ages 3 and 4, and they tend to produce only 1 beetle, so we had 10 times 1, and that turned out to be 10. So we add up the number of newborns, and what we find here is that we get 20 newborn beetles in 1 year. 200 newborn beetles in 1 year. Now, suppose we wanted to compute how many 1 to 2-year-olds. So suppose we wanted to compute how many 1 to 2-year-old beetles there will be after 1 year. So how many 1 to 2-year-old beetles will there be in 1 year? So to compute that, what we need to do is we need to consider the number of 0 to 1-year-olds that survive and become 1 to 2-year-olds. So this is basically a question about survival. So let's see, we had 30 beetles that were between ages 0 and 1. Their survival rate is 0.7. And so 30 times 0.7, that turns out to be 21. And we could continue this analysis to compute how many beetles there are between 2 and 3 years of age and so forth. But this gets a little bit tedious, and so it's going to be much more efficient if we look at encoding this in a matrix and we look at kind of what's going to happen in the long term, which ultimately leads us to an eigenvalue exploration. Okay, so let's set up a Leslie matrix. So we're going to set up something called a Leslie matrix. This is named after a biologist by the last name of Leslie, and he made these studies in about 1945, came up with this sort of matrix. So our Leslie matrix is going to look like the following. In the top row, so our first row, that's going to consist of the breeding rates. Okay, and then the second, third, and fourth rows, so second, third, and fourth rows are mostly zeros, except for what we call a minor diagonal, which contains the survival rates. Okay, let's take a look at the setup, and we'll actually see that this setup is going to perform the same computations that we just did up above. So our Leslie matrix, we're going to call it L. It's going to have 4 rows and 4 columns. The first row is going to consist of our breeding rates. So if we scroll back up here, our breeding rates, way up the top here, those were given as 0, 4, 2, and 1. So let's put those into our matrix. And then in rows 2, 3, and 4, we're going to have our survival rates on this minor diagonal. So we'll fill those in. And lastly, the 0.2, and that is our Leslie matrix. We also were given a set of initial conditions, and the initial conditions for this problem looked like 30, 35, 25, and 10. And so if we work through this computation, what do we notice? So we notice that the number of beetles in each of the age classes in the next time step, it's given by L times X naught. So let's write that down. It's our Leslie matrix, 0, 4, 2, 1, and a 0.7, a 0.5, and then our 0.2 for the breeding rates, times our initial conditions, And if we look at the calculations we're performing, the first set of calculations we perform, that's exactly the breeding rates times our initial numbers in each of the age classes. Okay, and that's going to give us the new number of newborns, and we determined that to be 200. And so I'm just going to put a note here. This was the number of newborns. Well, we usually don't refer to beetles as newborns, but we could say these are the 0 to 1 year old beetles. Okay, and then the next calculation that we do, we go through here and we look at this 0.7 times our initial condition, and the only thing that's really getting multiplied there is the 0.7 times the 30, and that's the survival rate of our newborns, and that tells us how many of them are going to grow up and become 1 to 2 year old beetles, and we already found that number to be 21. And so let's make a note here. These are the number of 0 to 1 year olds that grow up to be 1 to 2 year olds. Okay, and we can continue the analysis, and rather than crank through more calculations by hand here, let's hop over to MATLAB and compute the rest of these values. Okay, so let's continue here in MATLAB. So if we type in our matrix L and our matrix for x naught, we can compute L times x naught, and let's label that x sub 1. And so what we find the 200 and the 21, which we already found, but we also get 17.5 and 5 for our other components. So let's put those numbers in. We get a 17.5, and that may or may not make sense in terms of numbers of beetles, because how can you have half of a beetle? So it may make sense to take the floor function of that, or to round, depending on your application. I'll keep it in there for now. And the same sort of idea here is that the long-term trends, so if we want the long-term trends, we're really looking at finding those eigenvalues and eigenvectors, and we're actually looking for a very particular eigenvalue corresponding to a very particular eigenvector. All right, so let's write that down. We need to find the eigenvalue associated to the eigenvector with all positive components. Okay, so if we do that, and I won't show the details of doing that, but you could go to MATLAB or other software for that computation. So lambda equals 1.7923 approximately, and the eigenvector associated to that particular eigenvalue looks like the following. So we'll round to 4 digits of precision. We've got a 9267, we've got a 0.3619, we've got a 0.1010, and lastly 0.0113. Well, what does that tell us? That tells us a couple of things. It tells us the relative abundance of beetles in each of our age classes. So remember, this was our 0 to 1 year olds, our 1 to 2 year olds, and so forth. And viewing the numbers in this form isn't very intuitive intuitive or isn't very easy to interpret. So an easier way to interpret these relative abundances of the age classes is to normalize this eigenvector. And so to do that, we're going to take the sum of the components in the eigenvector. So we're going to add up these values, and in doing that, multiplying times our vector x, we get a vector whose components then sum to 1, and that's going to be a really nice result for us. So let's write down what we get. What we end up getting is we end up getting 0.6615 and a 0.2583 and a 0.0721 and lastly a 0.0081. And this is a nice interpretation because what this implies is that we have about 66.15% of the population in the age class 0 to 1 years old. We have about 25.83% in the next age class. We have about 7.21% in the 2 to 3 year olds, and lastly we have about less than 1%, about 0.81% in the 3 to 4 years of age category.